Hi students, we need to talk about the absolute acidity lab, the one where we did titrations. So first I want to go over a very simple acid-base titration. And this is the hydrochloric acid and sodium hydroxide equation here. So the hydrochloric acid is our acid and the sodium hydroxide is our base. And when we have a strong acid and a strong base and they react, what we're going to form is a salt and water. So if you guys have been watching the acid-base lectures, you already know that. And if you haven't been watching them, well, then you're going to go get to it right now, aren't you? Okay. So what's going to happen is we are going to try to figure out the concentration of some substance where we don't know the concentration by using another substance that we can react with it and we know the concentration of that substance. So in a titration setup, what we're going to have is we're going to have an Erlenmeyer flask down here. And usually in chemistry lab, we'll have an acid of unknown concentration. And then up here we have something called a burette. And the burette will have a clamp to make sure it stays upright, and it'll be standing on a burette stand. And what we're going to do is we're going to fill the burette, usually in chemistry class it's with a base, but whatever you're filling it with, it has to have a known concentration. So we're going to fill our burette up with base. And what we're going to do is we're going to read the initial volume. So that would be V sub I. And then we would open up the stopcock so that the base is dripping down into the acid. And as the volume goes down right there, we watch it. And then when we're at the end of our titration, we are going to note the V final. Now, the volume of base used that's going to be V final minus V initial. Okay, now how do we know when we're done with a titration? Well, you're going to put this thing called an indicator in with your a substance that you don't know the concentration of, and the indicator is going to change color and tell you when you're at the end point of your reaction. So for a strong acid and strong base, what we'll have is the end point around a pH of 7. And if we use the indicator phenolphthalein, what we're looking for is for it to be the slightest pink that we've ever seen. And if we overshoot it even a little bit, it'll get this dark pink color because the phenolphthalein is turning pink when it sees base. So if the solution as a whole is basic, then it'll be pink. If you just have a little bit of base dripping in, you'll see a little bit of pink. I guess that's blue. I should make it pink. Around where the base is dripping in, and then you swirl it a little bit, and those base molecules, they'll find acid molecules and they'll neutralize. And so if we get the slightest shade of pink we've ever seen, that's how we know that we're done with this titration, okay? So the question on the bottom is a practice question for us. It says you're going to titrate 20 milliliters of hydrochloric acid. So that is, come on pen, there we go. Okay, so we've got 20 milliliters of this thing, and it's an unknown concentration with 18.2 milliliters at 0.025 molar NaOH. So up here, we've got a known concentration, and that is 0.025 molar NaOH. And it says that the difference between V final and V initial is 18.2 milliliters. So say we started on an initial volume of 0.0, which you do not have to start on, and then you drained it down, it would have ended on 18.2. If you started your initial volume on 1.0, then your final volume would have been what to get a net volume of 18.2? Your final volume would have been 19.2 because you would have had to do 19.2 minus 1. Okay, so the question says, what is the concentration of your acid? All right, so this is how we're going to set it up. Now you've got 3 numerical values here. You've got 20 milliliters of your acid of an unknown concentration, and you have 18.2 milliliters of base, and you know the concentration of the base. So what you're going to do is you're going to start with the volume of a substance that you know the concentration of. So you don't want to start with the concentration. We're going to save that to use that as a conversion factor. And you don't want to start with a volume of the substance where you don't know the concentration because you don't have any conversion factors to get anywhere with that. So we're going to start with 18.2 milliliters of our NaOH solution. And whenever we're in milliliters and we're working with molarity, we're going to want to change to what? To liters. So we're going to let our units guide us, and we're going to have milliliters on the bottom so that milliliters and milliliters cancel out. And which one is bigger, the liters or the milliliters? Liters is the bigger one. So we're going to put the 1 up there. And how many milliliters can you get into a liter? 1,000. Okay, so now we are rid of our milliliters and we are in liters. So now you want another conversion factor, and you want to get rid of liters. So you need to put liters on the bottom here. Now, do we have anything in the question that relates liters to something else? Anything else so we can get out of liters? Yes, we do, because the big M is molarity, and that's the same thing as moles over liters. So what we have is 0.025 moles of NaOH for every 1 liter, and that is the exact same thing as saying 0.025 molar NaOH. Exactly the same thing. Okay, so now we're in moles of NaOH, and when you're in moles of something, you can go to moles of something else. This is what we called the multimole ratio a few chapters ago, and we've been using it over and over again. So we want to get rid of moles of NaOH, so we put it on the bottom, again letting our units guide us, and we want to go to moles of HCl, because in order to figure out the concentration of that hydrochloric acid solution, we need to know how many moles we have. All right, so I need a number here and I need a number here. Where do I find those numbers? I find them directly off the balanced equation. So that's why we need to make sure we balance things correctly. And if we balance this equation, we'll see that we have a bunch of 1s all the way through. And if you guys need to rewrite H2O as HOH, just so you can see the H and the OH, go right ahead. Okay, so for every 1 hydrochloric acid, we are going to react 1 sodium hydroxide. So those numbers right there are pretty easy. We've got 1 and we've got 1. And we're going to stop there and we're going to do the math really quick, and then we'll keep going. So moles of NaOH cancel out. All right, so when we go ahead and we do the calculation on this, we're going to get 0.000, so there's 3 zeros to the right of the decimal, 46 moles of HCl. And I did 2 sig figs because this value right here has 2 sig figs. But that's not the end of the question. The question says, what's the concentration? And if you're doing molarity, you have to do moles over liters, not just moles. So we've got 0.00046 moles of hydrochloric acid. And we want to do moles over a liter because that's molarity. So we're going to go ahead and plug that in. 0.046 moles of hydrochloric acid. And then we need to divide that by how many liters those HCl's were sitting in. And we have 20 milliliters, but that's not liters. So we need to switch that before we put that in the denominator down there. So we go ahead and we put 20 milliliters, and we have 1 liter and 1,000 milliliters on the bottom. And that's going to end up being 0.0200 liters. So we go ahead and we throw that in right there. So we have 0.0200 liters. So now we have moles of HCl over liters. So yay, now we have molarity. So if we use our calculator, what we are going to get is 0.023 mole per liter, and mole per liter is the big M, so molarity HCl. And the way that we say that is we have a 0.023 molar HCl solution. So I'm sorry about the jargon there, but that's how we do it. So that's how we figured out what the concentration of that acid solution was using the volume and the concentration of the base that was in our burette. Now that's not the end of the question because it says how many grams of HCl were present in the original solution. So this is one of our answers. Now we know how to go from moles to grams and grams to moles. So let's back up and use the moles over here. So we have 0.00046 moles of HCl. So we need to convert that to grams. So we're going to put 1 mole of HCl on the bottom, and we're going to put grams of HCl on the top. And that conversion factor is the molar mass of HCl. So you just pull out your periodic table and you go, okay, a chlorine weighs 35.45. And hydrogen weighs a little bit above 1, so let's go with 36.46 for this. Whiz bam bang, we do the calculation on this and we end up with 0.017 grams of HCl was in that original hydrochloric acid solution. So these types of calculations you'll see over and over and over again. They use the same pattern, but you have to keep your eye on what exactly it is that they're asking you for. Because moles will seem a whole lot like molarity, and how do I get to grams from there, and how do I get to milligrams from there. You can do it, you just have to really be paying attention to what you're doing and not be an autopilot on these ones, because there's a lot of moving parts here. Okay, so that was our example problem. So let's move on to what the lab is actually doing. So the lab is titrating acetylsalicylic acid, which is aspirin, with sodium hydroxide. So we're going to abbreviate acetylsalicylic acid as ASA because I don't want to keep writing that over and over again. And even though that is a big giganzo molecule, it's still an acid and it still behaves like the simple little acid HCl. It's an acid, so it's going to give away a what? An H+. So this is our acid right here, and this is our base. And the base, again, will be in the burette, and the acid will be in the Erlenmeyer flask. And we're going to create a salt and water. So H2O is our water. And over here we have the salt, but we're missing a little piece, and I wanted to draw that in for you because sometimes you'll just see the anion sitting there. So this is the acidic proton right here. That's what jumps off. So it gets together with OH minus. H plus and OH minus make H2O. And then you have Na plus just floating around in the solution, and it's really attracted to that minus that is on the anion from acetylsalicylic acid, and it's called acetylsalicylate, that anion right there. And it is a salt just like sodium chloride. But what we're used to right now in chemistry is that we always write the cation first and then we write the anion second. And also when we write the formula, we don't see the charges appear. But when we have a big old gnarly organic compound, and I'm not talking about organic as in like organic fruits and vegetables, I'm talking about organic as in organic chemistry, which is a carbon-hydrogen based chemistry. What we'll often see is the charges there, and we're pointing out that big old ion right there because it's something of interest to us. And we'll see the cation written second sometimes, but I don't want you to freak out over that. That's still a cation in an anion, even though the anion is huge. So when you have a cation and an anion together like that, we still consider it creating a salt. Okay, so here we go. All right, so you've got your aspirin tablets in the Erlenmeyer flask. You put a little ethanol in there so that they'll dissolve. And then you start titrating with your base. Now, your lab asks you the brand name of your aspirin. So sometimes in the lab, we have the original bottle out there. So maybe it's Bayer, or maybe it's Kroger brand, or whatever brand. Sometimes it's just in a clear bottle and it doesn't say anything. If you're watching the video and they don't say, then just cross out that line, okay? And then it says the molarity of your NaOH right there. That you are going to read off of the bottle. So if you were in the lab, you'd pick up the bottle and you'd go, oh, the molarity is 0.1001 or 0.956, whatever the bottle says. So I'm going to make something up. You guys are going to have to watch the video in order to see what your molarity of your NaOH is. And again, it'll be given to you somewhere. So again, I just made that up, 0.1779. All right, so maybe I fill up my burette with my base and I start at an initial volume of 1 milliliter, okay? And then I open up the stopcock and I let the base drizzle down into my acid, and I'm swirling my Erlenmeyer flask as I go. And once I reach the end point, it's going to be that lightest shade of pink that I've ever seen. And my final burette reading is 21.6. Now again, you guys, I'm just making this up, okay, as I go. You guys will watch the video to do this. Now it says volume of NaOH used. So the burette, how you read it, it starts with the lower numbers on top. So 0.0 or 1.0 would be on top. And then it would go down to 20.0 or 21.6, that type of thing. So the volume used would be 21.6 minus 1.0. So that would give me what? That would give me 20.6. So this is V final and this is V initial. And how I got 20.6 was I did V final minus V initial, and that gave me 20.6. All right, now the next line says volume of NaOH used, and you need to convert that to liters. So this one is in milliliters. So you guys should know by now how to get to liters. So I'll leave that up to you, but I'll go ahead and tell you what I got. And then it says grams of aspirin in 2 tablets. Now I'm going to assume that in the video they use 2 tablets. Some instructors like to use just 1 tablet. Some continue to use 2 tablets, but I'll let you know what we're going to do about that during calculation if they just use 1 tablet in the video. Okay. So how we're going to get grams of aspirin in those 2 tablets that we dissolved in the ethanol in the Erlenmeyer flask is this. We're going to do some calculations. So I'm going to start with 20.6 milliliters. You could start with 0.0206 liters, but I like to start with the milliliters. And when you're in milliliters, you need to convert to liters. So I'll go ahead and write that there for you guys. Cancel out the milliliters. Now I'm in liters and I want to go somewhere. So I'm probably going to use a molarity because that relates liters to moles. So I'm going to go moles of NaOH. And I don't have my molarity for my acid solution because that's what we're trying to figure out. But you do have the molarity of your NaOH. It's right here. We just made that up. Okay, so we cancel out the liters, and now we're in moles of NaOH. And when you're in moles of something, you can go to moles of something else. So we're going to let our units guide us and put moles of NaOH on the bottom here. And we want to get to moles of acetylsalicylic acid. So that means I better have this equation balanced. And if I take one of these and react one of these with one of those, it's going to give me one of these and one of these. So this was just like the first equation where all of your coefficients are 1. So we got really lucky here. But if our coefficients weren't all 1, we would mess up our calculations. So make sure that everything's balanced. So for every 1 mole of NaOH that I use, I'm going to react that with 1 mole of acetylsalicylic acid. Or you can say for every 1 NaOH that you use, you reacted it with 1 acetylsalicylic acid if the little mole word bothers you. Okay, so we're canceling out our moles of NaOH and we're in moles of acetylsalicylic acid. So in our practice problem, we stopped and we looked at how many moles we had. But with this problem, we're not going to stop here. We're going to go all the way through to grams because this part of the lab is asking us for grams. So we're just going to keep going. So we need to get out of moles of acetylsalicylic acid and we need to get to grams. And your lab instructions tell you, I believe they tell you, that there's 180 grams of acetylsalicylic acid per every mole. If it doesn't tell you that, I'm telling you that now, and you guys can Google that. Or you can add up all the carbons and hydrogens and oxygens in your acetylsalicylic acid and see that it's about 180 anyways. Okay, so we cancel out the moles of acetylsalicylic acid and we use our calculator in whiz bam bang. We're going to get 0.6596 grams of acetylsalicylic acid. And I want 3 significant digits. So, and I'll assume there's a little point there. So what I'm going to do is have 660 grams of acetylsalicylic acid. Now, that sounds really good because in general, each one of your aspirin pills is about 325 milligrams, which is 0.325 grams. So if we have 2 of those pills, what we're going to get is 650 milligrams, which is equal to 0.650 grams. And 0.650 grams is very close to 0.660 grams. So yay, we're pretty close. But anyways, this is the number that goes ahead and goes right here. 0.660 grams of acetylsalicylic acid. Now, if we were to only use one pill, your number would be close to 325. Okay, so now we have percent of a labeled amount of aspirin. And the lab manual does it a really funky way, and I don't know where the 648 instead of the 650 came from, but the people who wrote that lab have long since retired, so I can't ask them what's going on there. So I want you to do it this way. Go ahead and put your milligrams of acetylsalicylic acid on top, and then divide that by 650 and multiply that by 100. So what we would do for percent of labeled aspirin is we would say 660 divided by 650 times 100. And what we will get is 101.5%, or about 102%. So we'll put 102% there. And then you guys will go ahead and do a second trial, and you'll get another value there. And then you'll add those two up and divide it by 2 to get an average right there. And the USP says that you're allowed to be 5% off. So you're supposed to be 100% plus or minus 5%. So you are legal and within range if you are 95% to 105%. Now we got 102%. I'm assuming if we did another trial, we'd get pretty close. And both of those values would be between 95% and 105%, which is 5% off. And so my answer would be yes here. Now, if you got an average percent that was 107%, what would your answer be there? It would be no, because you would be 7% off, and that is outside of the USP guidelines. Okay, you guys, so that's how we do this lab. Enjoy.